Hello, good morning. Thank you all for coming after the banquet so early. If the screen works, then there we go. My name is Silvin Willemsen, and I will be presenting today for you the paper on real-time implementation of the dynamic stiff string using finite difference time domain methods and the dynamic grid, which I wrote together with Stefania Serafin. So my work is mainly on physical modeling of musical instruments, just like Ricardo. And the cool thing about this is that we now have the possibility to go beyond what is physically possible now that we have a virtual musical instrument on our laptops. So what we can do, for example, is change material properties of these instruments or even the geometry of the instrument in real time. So to, for example, morph a cello into a violin in real time, for example. So there's many ways to go about physical modeling, but a popular technique is called finite difference time domain methods. And as opposed to other physical modeling techniques, it's very general and flexible in terms of the systems that it can model. So you can have a very modular system, 4 strings and a body to make a cello, for example, which is easier to do with finite difference methods than, for example, other techniques. But the issue here is that it's very inflexible to parameter changes. So if you want to change the length in real time of the string, this is going to be hard with these methods. So in a previous publication, we aimed to solve this issue using something called the dynamic grid. And this is what the current contribution is also using heavily. So in the rest of the presentation, I'll first introduce finite difference methods and the dynamic grid. I want to spend a bit of time on that before going into the contribution, which is the dynamic stiff string, and end with a demo and conclude. So what are finite difference time domain methods? So these methods discretize directly partial differential equations. So say we have a partial differential equation here, for example, the 1D wave equation, where we have wave speed c here, and it describes a state u over space x and time t. And we can then directly discretize this to an FDTD scheme. So now you can see that space is discretized into discrete points, like space by n equally sized intervals. And it's also discrete in time. So we're stepping through time instead of here on the left, continuous PDE. So if we then expand the operators, I'm happy that Ricardo already explained this before, we get an update equation in the end. So we can see here time step k and grid spacing h here. And in the update equation, we see now that u at the next time step, indicated by n+1, is calculated based on known values of the grid. So here L is the spatial index along the grid. Now we have another variable here, lambda, which is defined as the wave speed times the time step over the grid spacing. This is referred to as the Courant number. And this needs to abide a stability condition, and it needs to be smaller than or equal to 1 in order for the system to be stable. So looking at different values of this Courant number, we can see that if it's equal to 1, so it satisfies the condition with equality, we get, in the 1D wave case, an exact solution. So this is very nice. If it's smaller than 1, we get effects such as dispersion, resulting in a lower bandwidth of the simulation. And this is something that we do not want. So reduction in quality, essentially. And if it's larger than 1, so it doesn't abide the stability condition, we get instability. And this is something that we definitely do not want because our system explodes. So ideally, we would like an exact solution, so lambda equals to 1. So from this condition, we can see that the parameters, so c in this case, the wave speed, is related to the grid through the stability condition. So what we usually do is we rewrite this condition in terms of the grid spacing. We have a desired wave speed, and we know our time step k based on our sample rate. So now we have a definition for h. So we can now also see that for a large wave speed, we need to deal with a larger grid spacing. For a smaller wave speed, we can have a smaller grid spacing. So now you can see if you want to change this parameter, how can you go from one grid configuration to the next? And this is where the dynamic grid comes in. And this is work that we published last year here at DAFx. And this allows for the smooth addition and removal of grid points based on these parameter changes. So what we usually do to calculate the number of intervals, so n, is to first calculate the grid spacing based on the parameters of the system, calculate the number of intervals based on the length of the system and the grid spacing, by using this flooring operation, because it needs to be an integer number of intervals. We recalculate the grid spacing, and finally we get our current number out. But what we propose in this previous work is that we now have a fractional number of intervals. So we remove the necessity of this flooring operation, remove the necessity of recalculating the grid spacing, and a nice side product of this is that lambda is always equal to 1, which is, if we remember, we want it to happen. So then the question is, how do we implement this fractional number of intervals? So what we do is we split the original system, U, into two subsystems, V and W. Then we have one grid point for overlap, which I'll come back to later. And these points are subdivided into MV and MW intervals, respectively. Then we have our outer boundaries, which are set to be Dirichlet boundary conditions, as you would usually also do with the normal implementation. And then here we have two inner boundaries, which are connected in a specific way, which I'll go into now. So if we expand the inner boundaries to their update equations, we can now see that we have two grid points here, which are undefined. They are outside of our range of calculation, so MV plus 1 and W minus 1. These are referred to as virtual grid points, and we need to find definitions for these in order to solve the system. So what we can do as a starting point is set these guys to be equal to the state of a point of the other system. So we can set VMV plus 1 to be W1, and the same for W minus 1 the other way. So if we take a look at a simulation here, we can see that this actually results in identical behavior to the original system. So we can say that this is at least a good starting point for our method. Then if we want to change parameters, so say we want to decrease the wave speed c, this decreases the grid spacing as well, according to this formula that we saw before. So what we do is we fix the outer boundaries in space, and then we move all the grid points towards their respective outer boundary. So if we zoom into the inner boundaries, we can now see that these grid points, they no longer overlap with a point of the opposite system. So we need to find alternative definitions for these guys. So what we propose in this previous work is that we use quadratic Lagrange interpolation. So we use values of the surrounding grid points to calculate the states of the virtual grid points based on these two formulas here. And here alpha, so the parameter used for interpolation, is essentially the fractional part of the fractional number of intervals, or how many times does the grid spacing fit between the inner boundaries. And we can take a look at how that behaves. We can see that the systems are still connected, albeit with slightly dispersive effects. But in the previous paper, we also showed that this is a pretty good result still. So then if we decrease the grid spacing, or the wave speed and the grid spacing even more, the virtual grid points surpass the inner boundaries. So now we need to start adding grid points to the system. And for that, we use cubic interpolation. So we use the surrounding states to create the new grid point. And this looks like this. We keep on decreasing the wave speed, and then at some point, a grid point will appear if it surpasses the inner boundary. Then removing grid points happens through simple deletion of grid points. So if the inner boundaries surpass each other, if we increase the wave speed instead, then we remove grid points in this way. Great. So now that we have this theory in mind, we can continue to the stiff string. And first, we have the non-dynamic stiff string, which Ricardo also showed in his presentation, where here we have the 1D wave equation, essentially, with a stiffness term added and some loss parameters. And this entire system is described by all these parameters. I'm not going to go into depth here, but later on, we will be able to change each and every one of these parameters of this system in real time. So then we discretize this to our finite difference time domain scheme. And the most important part, or the most challenging part here, is to deal with this fourth order spatial derivative, the stiffness term. So we can see here that now instead of only one neighbor for each grid point, we need two neighbors at each grid point in order to calculate the system. So if we want to apply the dynamic grid to this, we need an extra virtual grid point at either side of the system. So what are the definitions for these, and who's to say that the definitions that we found earlier still hold for these operations? So the trick is, if we go back to this slide, is to use a matrix form of the update equation. So we save the values of u in a vector, and then we apply matrix operations to update the state. And here DXX kind of encompasses this spatial derivative, this discrete spatial derivative here. So yeah, the trick is to write it in matrix form. So what we can do here with the stiff string is to save the states in a vector and write these guys in matrix form. So there's a lot of stuff going on here, but the most important thing is here that the DXX operator encompasses the spatial derivative. And this fourth order spatial derivative is simply, in the simply supported case, a multiplication of DXX by itself. Moving on to the dynamic stiff string, we again split the system into two. We now have V and W, and they, apart from V and W, they are identical. So also now the change in parameters here, we have a superscript n, which indicates that they can change over time. And then using this matrix vector formulation where we concatenate system V and W into one big vector, we can now define our update equation here in matrix form. The trick here, if we recall the interpolation operation from earlier, from the dynamic grid method, we need to encompass this somehow in our DXX matrices. So the way that we do this is we add here at the kind of, this is where the inner boundaries occur in the matrix, and we add this interpolation into the DXX matrix, essentially. And now comes the most important equation of the entire contribution, is that we can multiply this DXX matrix, including the dynamic grid method, with itself, and we get a definition for the fourth order spatial derivative with the dynamic grid method included. So this guy looks like a monster, so I'm not going to go into this, but these are the definitions for where the interpolation happens, and this is a visual interpretation of what happens to the virtual grid points based on the surrounding states of the system. All right, enough talking. Let me try and find a demo of this guy. So this is our stiff string, simply excited with a raised cosine. Can also excite it with the spacebar and start to change parameters. So here we have the length. The density. Radius. So you can also hear the inharmonicity increase, especially if we increase Young's modulus as well. Or if we decrease it to 0, we get the 1D wave equation back. Can increase the tension. And we have some damping coefficients here, so if we set them to be their minimum value, get a long resonation, and we can set them back to here. So we can test the limits, we can really go. And you can hear that these parameter changes are, well, fairly smooth. Like, they're almost instantaneous to go from one setting to the next. And in the background, there's grid points removed and added. I think the minimum is about 24 grid points, and the maximum is 1,500 something. So they get removed and added very, very quickly. Yeah, anyway, if you want to see more demo, you can come to me later. Cool, so in conclusion, we presented a real-time implementation of a stiff string with dynamic parameters. Future work, there's still occasional artifacts. So right now we're relying on especially frequency-dependent damping in order to reduce the artifacts that happen when especially removing grid points at the inner boundaries. It might happen that these grid points are very different in state when they are removed, so you get these artifacts sent into the system. But if you have enough frequency-dependent damping, you do not hear that. Of course, listening tests will have to confirm that. We want to define some stability conditions, so especially the interpolation at the inner boundaries, will that still be stable? And also the speed of variation. Right now, I think it takes a minimum of 20 samples before a grid point is added or removed, so we put a limit on that. But we still need to find stability conditions for that. Also multiple simultaneous parameter changes. So right now we only change one parameter at a time, but maybe we can interleave parameter like length and tension if we change both at the same time. And finally, full instrument morphing. Like right now we have just a changing string in real time, but what if you could do the visualization at the start, morph an entire cello to a violin in real time? And we actually already applied this method to 2D systems, so you can do the same matrix tricks for 2D systems, such as the thin plate. Might be able to extend it to 3D systems. We haven't tried that yet, but I don't see why not. And yeah, that's about it. Try it out for yourself. There's links to the releases on the GitHub repository. And I thank you for your attention.
Okay, thanks, Silvin. That was really good.
Thanks.
Any questions from the audience? Yes?
Very cool talk.
Thanks.
My question is the Courant number, like, how is that precisely defined? Is it supposed to apply to a regular grid or an irregular grid?
So for the 1D wave equation, the Courant number is just for a regular grid, so H is the same along the entire string. For the stiff string, of course, you have an entirely different definition, so H is bigger than or equal to square root of something big. It's in the paper. But yeah, that like stability condition is different for every system, but it applies to the like grid that is the same along the entire. Yeah.
So when you have an irregular grid, you kind of like ensure that it's satisfied, assuming it's regular on one half, and at the boundary, it's like satisfied, assuming that irregular grid is actually regular.
Yeah, so
or something like this. Yeah,
that is the future work that we still want to do. Like we want to somehow perform stability analysis on this matrix that we now formed. We did some preliminary experiments where we found that all the eigenvalues are on the unit circle. So that should indicate stability, but we still need to prove that algebraically. But there's good hope that this is indeed provably stable. Yeah.
All right, thanks.
Thanks.
Hi. Hello. Hi. Hello. This is Jakob from Music Tribe.
Hi, Jakob.
Thanks for the presentation. It's really impressive.
Thanks.
I must say you nailed the real-time part of this,
cool.
and within even a very impressive resulting sound. So I'm wondering about, do you have some heuristic roll-off in the frequency domain to fix the higher frequencies, or just limit it in some rule-based system, or is it part of the model? And also, the excitation when you play the string, in this case, it sounds like a pluck or something.
Yeah.
Is that a fixed excitation thing, and can you also maybe change the width of the plectrum, or is it a plectrum model?
Yeah, good question. Let me answer the second one first, and then I'll ask you about the first one. Right now, it's just we add a raised cosine distribution to both the current and the previous state of the system. So it's very unnatural excitation. It's like immediately pulling up the string and then letting it go. So obviously, we can do more work on having a better excitation, such as bowing or such as having a collision with an actual modeled pick. But yeah, the contribution was more about the resonator rather than the exciter. Of course. Oh, and you were asking about the higher frequencies. This is taken care of by the frequency-dependent damping, so the sigma 1 term. And the thing is, if we put that to 0, and you start to increase the wave speed so that these modes kind of go above Nyquist, then you get these artifacts. Like when they get removed from the spectrum, they put their energy to all the other modes. So which is why, I mean, heuristically, if the mode is damped before it exits the possible frequency domain, we have no artifacts. But still need to test that and still need to figure out a measure for that. But yeah, that's a good point.
Cool. Thanks.
Okay, we have time for a quick question where we do changeover. So I will invite the next speaker to come to the stage, please. Yes, Kevin.
Hello, thank you for the presentation, very inspiring. Kevin from Arturia. I have a question about the interpolation on the limits. How do you try it, choose the interpolation method you want to use, and which are the consequences of using other kind of interpolations?
Yeah,
on this?
good question. Is this still on? Or check, check, check. Yeah, oh, there we go. Yeah, we tried out many different interpolation techniques. We have all the odd-ordered interpolation, so linear, cubic, 5 times. Those in the second half of Nyquist, I can show you some figures that we made. The modes go up instead of down if you decrease the wave speed, for example. Only even-ordered interpolators get this nice smooth shape. The higher up you go, the more smooth it will become, but especially in the higher frequencies. So we thought the most flexible is the quadratic interpolation, because you can also place these inner boundaries close to the outer boundary and just have it kind of like when you tune your guitar up and down, just have it happen there. And the higher order you go, the more points you're gonna need at the edges of the system. So that's how we chose it. But we can talk after. I can show you some other interpolators.
Cool. Thanks.
Thanks. Thanks.